Okay, guys, I need us to consider another revision on our transistor amplifiers. This is a April 2024 exam where we are given our question transistor amplifiers on 3.1. Briefly describe the functions of the following components in common emitter amplifier used on a communication system. 3.11, the average, the voltage divider, RB1 and RB2. How are they going to be used? So the voltage division of RB1 and RB2 supplies voltage to the junctions of the transistor. Remember, when you have your transistor, you'll be having your RB1 and your RB2 at the input there, which is the one that is going to affect our transistor RB1 and RB2. As they supply the what? The junctions, these two. So they are for voltage division. So they supply the junctions. So these ones, like I said, they do supply. So they supplies voltage at to the junction. So you're gonna consider at the junctions or to the junctions of the transistor That is the major part that you must have there. And the input capacitor CB at the base, which is normally called C1, it blocks the DC signals. So it's going to block the DC signals, whereas AC signals are passed. So the AC signals are allowed, whereas the AC signals are allowed or they are passed. So that is the major part. For 4 marks, 2 marks for each, it was, I think it was fine, guys, for you to have those 4 marks with this simpler explanation. 3.2, you are given the following values. They are affecting a fixed bias voltage amplifier without thermal components are known. Okay, then we are given these values. So if we check properly, we are given this without thermal components. We are not having anything to do with the voltage division. We do not have RB1. We do not have RB2. We do not have all that part of the emitter effect. Remember, at the emitter there, you can have the resistor and also the capacitor, the bypass capacitor CE and RE. No. This part, they are not part of our circuit. They are not part of our circuit. This is a simple, basic fixed bias. I talked about that on the introduction. Make sure that you go through. So they were saying, calculate the following values: the collector emitter voltage, which is VCE. Okay? Which is VCE. So can we calculate VCE? Remember, we can do that. Actually, we do not have a formula where VCE can be calculated straightforward. But if we consider, remember, you're talking of the basic common emitter. So these calculations are not to be taken. These ones are when you're dealing with the voltage division, or when you are considering when there is emitter, resistor, where we now have the VE at the emitter there. So this time you must think of these formula, the basic ones, those basic ones from RC and RB. From RB, we do not have VCE, but from RC, there is VCE. From this one, we can see that VCE is there. So let's think along this. How can we obtain the value of VCE from there? Let's think along the RC. Okay, so that is what we're going to get. That is what we're going to have them. And we're going to try it and see if it is going to work. Okay, so that's 3.21. So from RC, we saw that RC can be given as VCC minus VCE. This is of a basic fixed bias, a basic one. Are we having these values? RC is given. The VCC is given. The IC is also given. So we can manipulate, make VC the subject. So this is over 1. Let's do cross multiply. So that's RC times IC is going to be IC. RC, which is equal to 1 times this. You multiply this by 1. It is going to be VCC minus VCE. Guys, you need to make VCE the subject. So it's a negative here. We can take it along across the equal sign so that it becomes a positive. The moment it jumps the equal sign there, it will be a positive. So VCE is equal to what? What are you left with on the right-hand side? You are left with the VCC. Then you take the ICRC this side. The moment you take it and crosses the equal sign, it changes to a negative. So it will be a minus. It was a positive, so it will be minus ICRC. So if you check on your memo there, it is just a mistake that was made to have a positive. Also, guys, these are transistors amplifier where you need to understand VCE that you're calculating. It's a voltage drop. This is just like a voltage drop across the collector emitter. From where? From here. From here. This is where it is taken from. From VCC, from. It is taken from there. So it cannot add here. So it was just a mistake from our formula sheet, from our memo. If you are using your memo, you can just say the plus there was just a mistake. It cannot add. The VCE is a voltage drop. It's less than. VCE is smaller than VCC because VCC is what? Is the supply. So you cannot have a VCE being bigger than VCC because VCC is what? Is the supply. So VCC is bigger than all the voltages. It is bigger than VBE. It is bigger. Any other voltage, is it VE, whatever, if it is to be, maybe there's a voltage divider because VCC is what? Is the supply. That is our fixed bias voltage. The one that is fixed as our supply. So you must be careful on that part. Anyways, let us see, because you'll be revising, then you are saying, okay, the memo is like, then you are like, you want to force that to be like that. No, guys, it's not like that. Okay, so just manipulate properly. So that's 20 there for the VCC. That is 20 minus ICRC. Our IC is 15. That's 14 milliamps. 14 times 10 to the exponent of minus 3 times RC, which is 1 kilo ohm. 1 times 10 to the exponent of 3. That was going to give us the value of VCE, which is 6 volts, which is less than VCC, the supply. VCE is less than, it is smaller than VCC because this one is the supply. Okay, so that's another part that you can also check your working. Then you can see, oh, this value is bigger. Why is it bigger like that? You check your calculations again under exam. So it's very, very wise that you do check all that. All right, so that is our VCE, which is 6 volts. Okay, the base current on number 3.22 IB. Do we have a formula straightforward that is used to calculate IB? We do not have, but we have RB that consists of the IB that we need. So we can manipulate that and make the subject. So you see, change of subject, guys, is something else in our engineering. You are supposed to be very good in your change of subject, in your mathematics, because that is almost like every part you need change of subject. So you're supposed to be very, very wise about that. 3.22, we saw that from RB, there is IB there. It's not direct. You're not going to have a formula always, which is direct and straightforward. No, they are not going to do that. Yes, it can be like that, but not always. So the IB that we want, which is the best current, is here. We can make it the subject. Again, big change of subject again, you see. Cross multiply. So that is going to be the product of RB and IB, which is IB. RB equal to 1 multiplies this. So it will be VCC minus VBE. Remember what you need to calculate is IB. So simply divide by RB both sides. You remove this RB by dividing by it. You divide by it. So IB was going to be given as this part, VCC, which is 20, minus VBE, which we are given as 0.7, all over RB, which we are given as 800 kilo ohms times 10 to the exponent of 3. So that was going to give us the best current. And our best current was going to be, when I have a bigger value there, 0.00002, 124125, something like that. And this can be converted. You can even convert to microamps. Just multiply by 10 to the exponent of 6. So by 10 to the exponent of 6 to convert to micro amperes, it means the answer is in now micro, which is 24. So it was going to be 24,125. That answer that you're getting on your calculator, automatically it is now in micro. So that is going to be microamperes multiplying by 10 to the exponent of, that was the conversion to micro. We are converting to back to the micro amperes, back to the micro. So that is the idea there. We have got your base current. Okay, so that is our IB could have been calculated using that way. So you not know, maybe we need this. So that was 24,125 microamperes. And with this information, they need us to calculate the beta gain. We need beta. That's 3.23. So remember that beta you're also given from your formula sheet, straightforward as IC over IB. You are given this as it is. So that's beta can be calculated because we have IC 14 milliamps. And we also have IB from our calculations, 24,125 microamps times 10 to the exponent of -6. That was going to give us the value of beta, which is our beta gain of 580,311, just like that. So that's your current gain in that case. So it can be like that. Questions can be given of that nature. All right, considering on question number 3.3, we are given that a supersonic radio has a fixed bias of a voltage. So it's a common emitter according to these values, HI, the E that we are given there, the E is showing that it's a common emitter amplifier. So they are saying we are given the input impedance, which is ZI, the input impedance 1,169 kilo ohms, and the output impedance is also given as 1,96 kilo ohms. And from this information, they are saying calculate the values of the collector resistor RC and the base resistor, which is RB. We need these values with the precise method. Precise method has to be used. If the information, the following information of the transistor is known, that is where you're given this information, and RS is equal to 0. Where we are not given on this information, we can see that RL is not given. And I said, if the load resistor at the output is not given, it simply tells us that the ZL will be equal to what? To RC. You take RC, which is your collector resistor, this one, your RC, as you had, remember your RC is 1 kilo ohm. You take that one as your ZL. Remember I talked about that guy. This is a basic one. So if it is like this now, the question is, how are you going to obtain RL, the RC and the RB? If we consider, because ZL and RC, they are equal, we can see from the input. I want us to get back to our input. Remember, on a basic. All right, this one, guys, there's a lot. So I need also you to be very, very careful with your formulas here. Z1, it consists of ZL, Z2. We do not have ZL there. But if you check, because we are given the input, at the input, this one, it is for this one is when it is a parallel, when there is that voltage divider. We do not have a voltage divider in this case. So Z in is going to be taken as what? RB parallel to Z1. Z in will be taken as RB parallel to, which is Z1 parallel to RB, because we do not have a voltage division. The voltage division is not there. Okay. So guys, there you have to be very careful. Let's be just stage by stage. So from Z1, let's see what was going to happen from Zi, from the input. The input is stating that Zi is supposed to be given from Z1 parallel to RB. Okay, of which I talked about that in our introduction. So make sure that you go through that, guys. Okay. ZB is RB. This one, the ZB is representing what? RB. Meaning, so you're talking of the product over sum. When you're talking of the product over sum, we're going to have Z1 times what? Times RB over the sum of Z1 plus RB. So if we check, we can see that in this formula, RB is there. RB is this, so that we need here is there. Z1, we have it, we are given. This is the input. What about, the ZI, this one, the input, ZI. What about Z1? The input impedance of the transistor only. From the precision method, how it was supposed to be calculated. I want you to see there now, our limit, how it was going to limit us. If you check, you were going to calculate your Z1 using this formula, okay? On this formula that we are seeing there, on calculating Z1, we can see that there is a ZL, and I say that ZL, because we are not given RC, it will be equal to RC. So definitely, as you want to calculate Z1, you are limited because you will need RC. Where RC is the value that we need also. Okay, let me write it. You will see, guys, how this formula was going to be limited. If you were to calculate Z1, you're going to say Z1 is equal to what? HI, according to the formula you are given. This is HF, HR. This is RC representing what? Representing ZL, because ZL is equal to RC. So this was supposed to be ZL. Okay, over 1 plus HO, RC, which is representing your ZL. So you will see that on this formula, RC is unknown. As we want to calculate Z1, you'll be limited again because you don't have RC, of which RC is the one that you want to calculate. So meaning to say, from the input Z1, there are too many limits. There are too many limitations that are there. So ignore that. Leave it like that. Move on to another one that can be worked with. Leave it like that. Let's move on to the output. From the output, let's check what's going to happen. Maybe we're going to have a solution there from the output. So you make this aside from the output. From the output, since we do not have RS and we do not have that part of RC, so ZL will just remain as RC as it is because we do not have RL, that load resistance. You will notice that at the output, Z out, the one that we are given, because we are given, we need to calculate from that. How are you going to calculate a Z out on a normal fixed bias? What is at the output? Remember, on that equivalent circuit, guys, I explained that at the output, you are going to be having Z2 there at the output, and you'll be having RC because you do not have any other resistor. So you'll be having RC and Z2. So Z out, it's a combination of these two, which are in parallel. The Z2 and the RC, because we do not have we do not have RL. So in that case, we are going to take our ZL to be equal to RC. So it is going to be Z2 parallel to RC. So RC is the one that we want. Remember, you need to find RC. So RC is already there. So meaning to say from this formula, it was going to be like this because it's a product over some parallel. Z2 times RC, or just write as Z2 RC, the product there, over the sum. That is in what? In parallel, over the sum. On this formula, RC is the one that we need to calculate, which is very true. Where Z out is given, this is our Z out. But we do not have Z2, which is the output impedance of the transistor only. We do not have that. That is where the precise method plays a role to say, how are you going to calculate Z2 by precise method? Our Z2 was supposed to be calculated from this formula. Are we having everything? If we check this formula for Z2, everything is there. We are not limited because we are told that RS is what? It's a 0. So it was easier to work from the output than to work from the input because the input is limiting us. We do not have the ZL, which is our RC. So it was going to limit you. So it's exam, guys. You have to figure out like that. You have to figure out. So you see that, okay, from the output, there is something that can, that is workable. So I need to calculate Z2 because Z2 is direct. And we saw that our Z2 from our H parameters, it's going to be 1 over what? That is HO minus, so the formula, guys, we are given, that is HF, HRE over what? That was going to be HI plus RS. This was supposed to be our formula. And in this case, you are told that RS is equal to what? It's a 0. So there's nothing to substitute for RS. So let's substitute everything. We calculate our Z2. So Z2 is straightforward. So it's going to be 1 over HO. These are the values that we are already given. So you're going to substitute your HO, which is 20 micro. So that is 20 micro, 20 times 10 to the exponent of minus 6 minus, we're going to have a fraction. In this case, having HF and HR. So if we check our HF, that is 16. Our HR is 2 times 10 to the power of minus 4. So we're going to have 60 times our HR, which is 2 times 10 to the exponent of minus 4. Everything that we are obtaining here is divided to HI plus RS, where HI was given as 1,2 times 10 to the exponent of 3 plus our RS, where we are given, remember, that's a 0 there. We do not have resistance of the source. So that was going to give us Z2, which is 100,000 ohms, equivalent to 100 kilo ohms. Calculating Z2 helps us now to have the value of RC. So in this case, it's easier for us to find RC. So let us just find RC, because we're simply going to make it the subject of the formula. Yes, you can substitute here as it is, it's fine. Or you can make it the subject of the formula because we have this. So let's make RC the subject. So make RC the subject. Making RC the subject, this is over 1. So we're going to cross multiply. Z out multiplies everything that we are seeing. So it's Z out times Z2, which is Z out, Z2. Z out multiplies also RC. So it's going to be plus Z out RC. You multiply everything by Z out. 1 multiplying Z2 RC. So it's going to be equal to Z2 times RC, which is same as what? Which is same as Z2 RC, like that. So that's where we are. And we need to make the RC the subject, this one. So let's collect the terms with RC to one side of the equation. Can transpose this, becomes a negative. It's up to you the way that you want to transpose there. So it's going to be Z out. Z2 is equal to what? Z2 RC already on the right-hand side. Transposing this gives us a negative because it was a positive. So it's Z out RC. RC is common and it is the one that we need to calculate. So we can factor it out. Remember your N4 mathematics, you obtain Z2 remaining minus ZO, which is equal to ZO, Z2. What is it that you need? It's RC, so simply divide by the bracket. That's it. So you simply divide by the bracket. That's obtaining RC. So RC is equal to this Z out, which we are given the output impedance to be 1,96 kilo ohms. So you're going to substitute 1,96 kilo ohms times 10 to the exponent of 3 times Z2. From our precise method, our Z2 is obtained 100 kilo ohms. Everything over what? Z2 minus Z1. Remember your Z2, 100 kilo ohms minus Z1, which is this minus Z out, Z out, which is 1,96 times 10 to the exponent of 3. This was going to give us the value of RC, which is 1999,184 ohms. You have the value of RC, collector, resistor. Okay, so that is how we could have ended up with our RC from this calculation. So let's see. Since the first formula, we were limited because we're not having RC. Now that we have got our RC, let's try and manipulate our formula to calculate the remaining part, which is RB. Okay, let's see. Because as I introduced here on the first part, that from the input, we saw that we were limited because one, we were not having RC in order for us to obtain Z1 by precision. So now we can calculate Z1 because RC is there. So it's going to be HI. Just substitute. Your HI is 1,2 kilo ohms. 1,2 times 10 to the exponent of 3 minus HF. Your HF, which is 60, you're given, that is 60 from this information. That's 60 times your HR, which is given 2 times 10 to the exponent of minus 4. That is 2 times 10 to the exponent of minus 4 times RC, the one that we just calculated right now, which is 1999,184 over what? 1 plus HO, as it is given, 20 micro. 20 times 10 to the exponent of negative 6 times RC again, as it is 1999,184. So this is what you're going to have. This one is a single part. With this combination, definitely you are going to obtain the value of Z1, the input impedance of the transistor only, which is 1,176,932 ohms of the transistor only. With this, we are going to now use it to determine or to find our RB at the input, because we saw that Z1 can be related. So again, we're going to make this the subject, guys, just like what we saw. You cross multiply, just like the previous case, we're going to end up with RB at the end as Zin times Z1 over the difference of Z1 minus Zin. So you are going to make RB the subject, cross multiply, then you collect the terms of RB, factor out, just like the previous case, guys, you're going to have the same answer like this. So with this now, you can find the value of RB by substituting the values that we are having. Zi at the input, 1,1691 kilo ohms. So this is 1,169 times 10 to the exponent of 3 times Z1 as we obtained it here. Our Z1, 1,176,932 over what? Z1 minus Zi. So our Z1, 1,176,932 minus Zi at the input, which is 1,169 times 10 to the exponent of 3. This was going to give us the value of RB, which is our base resistance that is affecting the whole part of the base, which is 173,453,543 ohms. So just like that, you can even convert to kilo ohms, divide by 1,000. It's up to you. You can just leave it like that. So this is how questions can be like. They now know that you are used to these formulas. You're just taking this direct as it is. Now they want you to manipulate the formula that you are used to from your precision, the precise method. Try by all means to play around the formulas where these quantities are hidden. The RC is hidden. The RB, where are they hidden? In which formula? They will hide it in another formula. Try to plug it out and see how we can find out the value. So they are now avoiding us to just have a direct formula where they will just ask you using a precise method, calculate the value of ZI, calculate the value of Z out. You are used when you are the one who is calculating that. Now it's a reverse to that which you are used to. It's a reverse to that which you are used to. So I need us to revise as much questions as we can. Then we shall meet again in another class as we are working on our industrial electronics N5.